at properties of ionic compounds. The learning intentions of this video is we're going to be first reviewing over things we've covered through about ionic compounds as well as ionic bonding, and then looking at how we could actually write the ionic formula. So we're going to do a bit of revision, and then I'll be administering a pop quiz for you guys to actually complete. And lastly, we're going to be looking at physical properties of ionic compounds, and we're going to be explaining why this is the case in terms of its structure as well as its bonding. So firstly, we said that ionic compounds are essentially a group of atoms made up of charged particles. Ionic compounds are made up of cations, which are positively charged ions, as well as anions, which are negatively charged ions. By having these positive charge and negative charge ions together, they essentially cancel each other out in terms of the net charge. So the net charge of an ionic compound is equal to 0. Ionic compounds are formed when metals actually donate their valence electrons over to the non-metals. Metals have a tendency to lose electrons because they want to achieve electronic stability. By losing the electrons, it will now become a cation because it will have more protons than electrons. In contrast, the non-metals will accept the electrons from the metals, and by doing so, it becomes a negatively charged ion, in other words, an anion, and it will now also have a complete outer shell. This is kind of illustrated in the diagram I have on the right-hand side over here, where you can see that sodium, which is a metal over here, transfers its valence electrons, meaning its outermost electrons, over to chlorine, which also requires one extra electron in order to achieve electronic stability. By doing so, you can see that the net charge of the sodium now becomes positive, and the net charge of chlorine now has a net charge of -1. We also said that ionic compounds are these electrostatic forces of attraction between the cations and anions that occur due to these electron transfer processes. Now, in terms of predicting the charges of monatomic ions, we said that this can be done by looking at your periodic table and then determining how much electrons that particular element needs in order to have a complete outer shell. So, for instance, we said that nitrogen over here belongs in group 5, therefore it has 5 valence electrons. It needs to obey the octet rule. So, therefore, in order to have a complete outer shell, nitrogen is going to be gaining an extra 3 electrons, so it has 8 electrons on its outer shell. So therefore, by gaining extra 3 electrons, and remember electrons are negatively charged, therefore the net charge of nitrogen is going to be 3 negative, and we always write the number first, followed by this charge afterwards. Fluorine, on the other hand, is a halogen. It is found in group 7. It has 7 valence electrons on its outer shell, so it will therefore gain 1 extra electron. Therefore, it's going to have a net charge of -1. And calcium belongs in group number 2 over here. It's got 2 valence electrons. It's going to lose 2 electrons because it's more easier to lose 2 as opposed to gaining an extra 6. So therefore, calcium is going to have a +2 charge over here. So that's how we write or determine the ionic charges of monoatomic ions. When we're looking at, or when we're trying to actually find out the ionic charges of transition metals, previously I discussed that transition metals kind of obey very differently. So it's a bit hard to predict what its charge is just by relying on the periodic table. To kind of get around that, what questions often give you is they actually tell you what the charge is in Roman numerals. So you kind of need to know your Roman numerals, just pretty much 1 to 4. In this case over here, when there's a Roman numeral associated with a particular transition metal, that means that that particular transition metal can have multiple charges. It could either have a +1, +2, +3, or +4. It's always going to be positive charge because although it's still classified as a metal, metals have a tendency to lose electrons. So firstly, looking at our first example of here, silver Ag+, notice that there's no Roman numerals associated with this, so therefore silver only exists in this particular state when it does form an ion. Copper 2 over here, so therefore it's going to be copper 2+. Copper could also be copper 1, copper 3 as well, so just keep that in mind. Iron 3, therefore it's going to be Fe3+. When you're trying to find out the ionic formula of these particular transition metals, remember we do the CRISS-CROSS method. So this is Fe3+ over here. Chloride is essentially Cl-, so therefore do the CRISS-CROSS method, and therefore this is going to become FeCl3. In this case over here, because Cl is a monoatomic ion, we don't really need to include the brackets at all. It's only when you have polyatomic ions, meaning you've got a group of atoms that form an ion. So more than 2 atoms that form an ion. This is copper 2, so Cu2 plus. Sulfate is SO4 2 minus. Notice that the charges of each of these are the same, although they're just different opposite signs. So one's positive, one negative. When they have the same sign, this can be simplified to pretty much 1. So therefore, this would therefore be SO4 like this. And therefore, this one over here is going to be Cu bracket NO33 like this, because this is Cu3, nitrate is NO3 minus, crisscross, therefore that should be your answer. When we were naming monatomic ions, we said that the first part, which is generally the metal in this case, their names does not change at all. So therefore, in these examples up here, when sodium forms the sodium ion, notice that all I've done is just include the word ion after its name to differentiate between a neutral sodium atom versus a sodium ion. Similarly, for magnesium, you just add in the word ion afterwards. When we're naming the non-metallic anions, what we do need to do is we need to actually change the suffix of the actual name to the word "ide." So in these examples here, fluorine, when it does become an ion, so when it does gain an extra electron in order to become stable, it becomes fluoride. Similarly for sulfur, this part is now changed to I, so this becomes sulfide. You do need to know these common polyatomic ions. So this is something that you should have already copied down in previous lessons. So please make sure that you kind of are familiar with these ones over here, because these are the most common ones that you will encounter. When we're naming ionic compounds, we previously said that we always need to write down the metal ion first, because this is the writing convention. You always get the metal followed by the non-metal, and then just change the suffix of the non-metal part. So for instance, for CaBr2, Ca is calcium, so that's the metal component. That's therefore just going to become calcium. Br is bromine, but we need to change bromine to bromide. So therefore, the first example is going to be calcium bromide. Ally is lithium. O is oxygen. You need to change the O part to an ide. So therefore, this is going to become lithium oxide. Al is aluminium. O again is oxygen. Just change it to ide. So therefore, it's going to be aluminium oxide. We said that there are two ways for you to actually determine the chemical formula of ionic compounds. So the first method is by either doing it the long way, where you have to draw the electron transfer processes and then count how many atoms are there at the end. So for instance, in this case over here, we looked at this particular example. So after you've actually drawn it, notice that you've got one lithium atom with one chlorine atom. So therefore, it's going to be LiCl. For part B, where you've got beryllium and fluorine, notice that you've got two fluorine anions and you've got one beryllium cation, so therefore it's going to be Be, just one Be, followed by two Fs. And you have to put that 2 as a subscript, so the lowercase in this case. Potassium sulfur, this will become therefore K2S, and magnesium and oxygen, when they form an ionic compound, it will just be MgO. Now, the easier way to actually find out what the ionic formula is going to be is by actually following the CRISS-CROSS method. So what we need to do is firstly identify what are the charges of each respective ion. So aluminium, when it forms an ion, it will therefore become Al3+, because it's in group 3. Sulfate, if you kind of refer back to the table that you've copied down earlier, this is SO4 2-. So by following the CRISS-CROSS method, so you're only exchanging the charges. This will therefore become Al2. This doesn't require a bracket at all. So because Al is a monatomic atom, so you don't need a bracket at all. However, you do need to have a bracket for the sulfate, because sulfate is a polyatomic ion. So therefore, you need the bracket, and the 3 goes down over there. This is a common trap that I kind of didn't go through in the last lesson, but I do want to go through it now. It reads out, since the writing convention is the cation is written first, followed by the anion, one of the ways that question might want to throw you off is by giving you the actual non-metal first before the metal. So for instance, they might say, write the ionic formula between oxygen and potassium. So when these two elements over here, they form an ionic compound, write down the ionic formula. So in the previous examples over here, notice that if you go back to the other slide, notice that I've always given out the metal first, followed by the non-metal, because that is just writing conventions. However, in this particular example over here, they've actually given you the non-metal first, followed by the metal. So Again, we can still do the same working out method. So write down the individual ions for each respective element. So in this case, oxide is O2 minus, potassium is going to be K plus. That's a typo over there. Then you need to exchange the charges, so therefore this becomes OK2. Now, although this is kind of correct, this does not follow the typical writing conventions. So therefore, because this is a non-middle first, so therefore we'll just pretty much swap the order around. So therefore it's going to become K2O. This is therefore going to be the correct answer. All right, so what I'd like you to do now is to answer the following warm-up questions. So please pause the video right now so you can attempt them before checking your answers with my solutions to the warm-up questions that you just did. So first question, you need to write down the ionic formula for the following pairs of ions when they form a compound. Now, for these three examples over here, I've actually kind of used that little trap question where I've actually given you the anion first, followed by the actual cation. So remember, when we're doing our writing conventions, write down the metal, which is often the cation, then the anion. So to avoid this, lithium is Li plus, carbonate is CO3 2 minus. Now we'll use the CRISS-CROSS, we use that technique over here to actually find out the ionic formula. So therefore, this is going to become Li2CO3. Hydroxide is OH minus. Aluminium is Al3 plus. So therefore, use a crisscross method. This now becomes Al bracket OH close bracket 3. The reason, again, why we use brackets over here is because hydroxide is a polyatomic ion. So polyatomic ions are ions that contain two or more atoms. Chloride is Cl minus, magnesium is Mg2 plus. So therefore, the ion formula of magnesium chloride will therefore become MgCl2. The second question, you need to write down the ionic formula, but also you need to state what elements are present, as well as count how many atoms are there for that particular element. So for the first example, sodium phosphide, if you've successfully followed the crisscross method, you should get your ionic formula as Na3P. This lowercase 3 over here, this subscript indicates there are 3 sodium atoms and there's only one phosphide because there's no number over here, which kind of means there's a 1. So in this case, the way that I'd answer this is I'd go 3 times Na and 1 times P. Magnesium over here is Mg2 plus. Nitrate is NO3 minus. Follow the crisscross method, so therefore it should be Mg bracket NO3 close bracket with a subscript 2. We can see that there's only one magnesium. However, when you have a bracket over here, what you need to do to count the number of atoms present inside of the bracket is you actually need to multiply. So what you need to do is you need to multiply 2 with the number in front of, or the number of nitrogen atoms. In this case, if there's only one nitrogen, so 2 times 1 is 2. So therefore, that's how I got 2 nitrogen atoms. And to get the number of oxygens, you need to multiply this outside number 2 with this subscript over here 3. So therefore, there are 6 oxygen atoms in total. Lead is therefore going to be Pb2 plus. Sulfur is SO4 2 minus. Now, because they have the exact same charge but just pretty much opposite signs, they cancel each other out essentially. So therefore, this is pretty much a 1-to-1 ratio. So therefore, it's going to be PbSO4. And therefore, we can say there's 1 lead atom, there's 1 sulfur, and there's 4 oxygen atoms. Ammonium is NH4 plus. Sulfur is SO4 2 minus. So again, exchange the ionic charges. So therefore, this 2 goes over here. Because that 2 goes down to a polyatomic ion, we need to actually include brackets. So therefore, the way we write this is NH4 close bracket 2 SO4. If you do this exact same thing for the other 4 questions, these are the answers that you should arrive with. So please make sure you check your answers and got the same answers as mine. All right. After you finish those questions, what I'd like you to do right now is I'd like you to spend the next 20 to 40 minutes working on this particular pop quiz. So this pop quiz is quite lengthy. It will take you a considerable amount of time to do it. There's about 30 plus questions or so, but they're all multiple choice, so it shouldn't take you too long. And they're just going to go over topics such as ionic bonding, ionic compound, writing the formulas. So this should take you fairly... it won't take you too long if you actually understood most of the things that I've already covered in this particular video over here. I highly recommend that you redo this particular quiz if you're not getting above 70% on your actual Google Forms. So please take your time, good luck with it, and once you finish that, then please continue watching this video. what I'm going to be doing now is we're going to be going over the structure of ionic compounds. So what I have over here, these diagrams I have on the right hand side, these are the structure of an ionic compound in the solid state, okay? So when it's in the solid state, ionic compounds have a crystal ladder structure. What do I mean by a crystal ladder structure? A crystal ladder structure is a 3D ordered grid-like arrangement. The reason why I said it's ordered is because, as you can see by the diagram on the right hand side, notice that it is highly structured. It is in this nice as organized arrangement. So they have this fluorine atom over here, followed by another lithium, followed by another fluorine. So they have this nice, neat structured order to it. That's why I've said it's an ordered. And they have alternating anions and cations, as you can see as well. The cations and anions present in this ionic compound are held together by these strong electrostatic forces of attraction, aka the ionic bonding. So looking at in this particular model over here, all the lines over here, these indicate the electrostatic forces of attraction, aka the ionic bonding forces of attraction. So these are the attraction between the positive and the negatively charged ions. Now, the physical properties of ionic compounds can be pretty much explained based on its structure as well as the type of bonding present in it. So now we're going to be looking at the properties of ionic compounds. Now, ionic compounds have the following properties. They are hard and brittle. So the word brittle over here means it's essentially hard. However, they can break very easily. Like glass is brittle. Ionic compounds also have very high melting and boiling points. They're also extremely good electrical conductors only when it's in the dissolved state or when it's molten in the liquid form as well. It cannot conduct electricity when it's in the solid state. In addition, only some ionic compounds are water soluble, so that means it can be dissolved in water. That's only for some of them. You're going to learn this in a bit more detail in BCA Chemistry Unit 2, but for now, all you need to know is just only some ionic compounds are water soluble, not all of them though. So, but what you do need to know is that you need to pretty much know that these three main ones over here, and you're expected to explain why ionic compounds have the following characteristics. So that we're going to be doing that right now. So please make sure you copy down these notes over here into your exercise book. Alright, the first property we're going to be looking at is why do ionic compounds have high melting point? Now, I want to clarify that melting point is essentially when the temperature to convert from a solid to a liquid state, okay? So what is the temperature to convert from a solid to liquid? We say that ionic compounds have these very high melting point because they have these cations and anions that are tightly packed together due to these strong electrostatic forces of attraction. So the positive ions and negatively charged ions are extremely attracted to each other. So it's going to be really, really hard for you to kind of break them apart. You're going to need a lot of thermal energy. So pretty much you need high temperatures in order to break those ionic bonding. When you break those ionic bonding, these cations and anions are therefore free to move, and when they're free to move, they're therefore in the liquid state. So again, just to kind of summarize that, this is pretty much what an ionic compound would look like if it was in the solid state. Again, it's in this fixed arrangement. They don't move at all, and they're tightly packed. When you crank up the temperature, the particles start vibrating, and then when you exceed the when you put up the temperature to its melting point, eventually the particles are able to kind of dissociate from each other and they can move freely. And when it's at that point, it's in the liquid form. In the table that I have over here, I've got the melting points of various ionic compounds. As we can see over here, they've got extremely high temperatures. For instance, this over here, NaCl, sodium chloride, this is table salt over here, and we can see that it requires 801 degrees Celsius in order for you to actually convert a solid sodium chloride into its liquid form, which is quite ridiculous. Alright, we're going to be explaining why do ionic compounds conduct electricity when it's in the dissolved or molten state. Before that, we're going to be revisiting what are the conditions for any substance to conduct electricity. We said that a substance can conduct electricity if it has these two characteristics or these two conditions. Firstly, you need to have charged particles in the substance. And secondly, those charged particles must be able to move freely. So therefore it's mobile, and when it's mobile, it can therefore carry an electric current. What I have on the left hand side is the lattice structure of an ionic compound in the solid state. Again, you can see that the cations and anions in the solid state are in these fixed positions that are tightly packed with one another due to these strong forces of attraction. However, when it's in the molten state, we can see that the particles are therefore free moving. Now you've got a scenario where these charged particles are able to move and therefore carry an electric current, which is why when ionic compounds are in the liquid state, or when it's dissolved, it can carry an electric current, whereas in the solid state, it is unable to, since these ions cannot move at all. So just to summarize again, in the solid state, the cations and anions are in fixed positions, therefore it cannot conduct electricity. In contrast, when ionic compounds are dissolved or melted, the cations and anions are free and can move around, therefore it can conduct an electric current. And I've got this diagram over here, another diagram to show how that kind of works. Now, I also have another diagram over here which kind of explains why ionic compounds can conduct electricity. So what I have here is a circuit. So remember, we were creating circuits for our previous prac. You're doing something very similar over here. What these things over here, these are pretty much what we refer to as electrodes. These are pretty much it's a type of substance that allows you to conduct electricity when you're submerged in a beaker. So in this beaker over here, you've got a solution. So pretty much a solution of KCl, potassium chloride. This means potassium chloride is dissolved from this water beaker. And it's in its ionic form, okay? So the ions are freely moving. Now, when you have an electric circuit attached and connected to this solution containing potassium chloride, what happens is that the ions can actually move and pretty much complete the circuit. So for instance, over here, you've got electrons moving from the power source down this electric circuit over here, and it'll move in this particular fashion over here. Now, once it reaches the electrodes, something fascinating happens. The electric current can kind of be passed on to the ions that are present in the solution, and these ions can move across to the beaker and then carry the electric charge over to this electrode over here, the negative electrode, to therefore complete the circuit, and by doing so, this can therefore conduct electricity. So this is going into a bit more detail. You don't really need to know this at all, but you will see this a lot more in year 11 and year 12. For now, all I need you to do is pretty much just copy down these notes over here to explain why ionic compounds can conduct electricity. Alright, we're now going to be looking at why ionic compounds are hard. So for any material to be classified as hard, the reason why it is because at the atomic level, the particles are compact and tightly packed. So in an ionic compound, due to the strong electrostatic forces of attraction, this is why ionic compounds are tightly packed, and because they're tightly packed, they are therefore considered to be hard materials. Ionic compounds are brittle. Now, what I have over here is a really good diagram that kind of explains why ionic compounds are brittle. So over here, this is an ionic structure of an ionic compound in the solid state. Now, when you're applying a force, so let's say that I've got a hammer and I've applied a force onto the actual crystal structure of it, what happens is that this disrupts the layer structure and shifts the layers. So over here, you can see that I've moved down these two layers down one slot, okay? Now, by shifting the lattice layers, what happens is that this now aligns like charges together. So can you see that these two positive charges over here are now side by side one another? These two negative charges over here are also side by side with one another. By having these light charges directly across from each other, what happens is that this now causes electrostatic repulsion. So this is the opposite of electrostatic attraction. Repulsion means they repel, they break apart, and this therefore breaks the lattice structure into different pieces. Therefore, this explains why ionic compounds are brittle, why they break so easily when you apply a force, because you cause the like charges to align with one another, which therefore causes electrostatic repulsion. Please copy down these notes over here into your exercise book, because this is a really good summary to explain why ionic compounds are brittle. After you've done that, I want you to please answer these review questions for me over here. If you need any help, then please ask me on the WebEx meetings group chat. So the first question reads out, what does crystalline lattice structure mean? So please refer to the notes that you've covered earlier on to address these questions. Once you've actually finished answering these review questions, I'd like you to quickly go on and answer some multiple choice questions on that's related to properties of a compound. So there's a link over here, but also it's also found on Google Classroom. So please answer this. This will take you no more than 5-10 minutes. There's about like 15 multiple choice questions, which shouldn't take you too long. This is the end of the video. Thank you guys for watching. Leave a thumbs up if this video helped you. See you in the next video.